For our next presentation, the speaker is Murad Anavaram from University of Southern California. He is a faculty member there. So let's give a moment to set up. Right, and the topic of the presentation is Edge Private Graph Neural Networks with Singular Value Perturbation. Over to you.
Good morning, folks. My name is Murali Anuvaram. I'm a faculty member at the University of Southern California in Los Angeles. So today I'm presenting the work on behalf of my student who is unable to attend the conference due to visa issues. So here I am. I haven't presented in a conference in a long time, so please pardon me if I forgot how to present it properly. And so with respect to the talk today, we're going to focus on edge private GCNs with singular value perturbation. And so it's funded through NSF, DARPA, VMware, and we have a USC Meta Center that's also funding this work. And so with respect to the outline, I'm going to present some motivation of our work, some background, followed by the Eclipse technology that we developed, and then the experimental setup and results will be presented at the end. So graphs are everywhere. They're from social networks to financial transactions that exchange between institutions, as well as molecular structures and used in sort of new drug discoveries and so on. And so graphs are present everywhere. And so the issue is you want to learn from these graph structures such that you can figure out what sort of information is hidden in these very large structured graphs. And so one way to learn from these graphs is using graph convolutional neural networks. And what is graph convolutional neural networks? Graph convolutional neural networks basically take two inputs. One is the set of features associated with each node in the graph, and the second one is the structure of the graph itself. So for example, the adjacency matrix that shows what are the nodes connections, and the output, for example, is a node classification. It basically says that this node is a particular type of a node. And so to kind of give you a brief pictorial introduction, so here is a graph, and you can collect the adjacency matrix by connecting the graph, by extracting the edges from the graph. And then you have a features associated with the nodes. So, certain elements that you already know about each of these nodes. And you feed these two things into some sort of a GCN layer, which basically performs certain computations, which takes the matrix A and also the feature X, and computes with and uses a learned parameters W and produces an output called the hidden features. And then you can continue to do this multiple layers, and eventually you will get the node classification output from this system. And so you can kind of train these systems so that the W is learned over time. And so this is pretty standard process. Many graph convolutional neural networks exist in literature today. And so the question is, these are very popular. So what exactly is the problem with these graph structures and using these in the GCNs? So the issue is that the GCNs are using graph structure, and graph structure is sensitive information. So for example, I don't necessarily want to know who I'm talking to or who I'm connected to on my social network. And so same with many of us who are worried about our privacy, and these structures expose substantial information about who we are in the society. And so let's take a look at what can a adversary do in a system. So for imagine that you have a matrix A, which is the adjacency information, and you said, I'm not going to provide this matrix A to an adversary, but they have access to the GCN that is trained. So this is a pre-trained model. You provide the GCN to the user, and they can essentially query the system many times. So they basically can ask many questions to this GCN multiple times. And so if an attacker can access essentially the node features and the output of this GCN, they are able to actually go back and reverse extract the adjacency matrix. And there have been studies that demonstrated that one can extract the matrix, adjacency matrix A, using basically called a black box attacks, where you don't even know anything about the matrix A, but you can actually just probe the GCN enough times to extract this information. And this is a problem. So how do we protect the adjacency matrix A? So one way to protect this adjacency matrix A is to actually not have adjacency matrix A inside your training system itself. And so now you want to protect A by not disclosing this A to the system. And how would you do that? Differential privacy. So if you attended session 3B yesterday, there were a whole bunch of talks on differential privacy. If I was giving the talk there, I could avoid the next 5 slides, but for the benefit of those who haven't attended session 3B, I will give you a brief overview of what a distorted differential privacy looks like. So what is differential privacy? So here is a adjacency matrix A with a particular graph, features given to a GCN, and it produces basically the node classification distribution information. And then what differential privacy does is it basically adds or subtracts one edge from this matrix. So basically take this adjacency matrix and we essentially flip one bit, 0 to 1 or 1 to 0, and then you get a new matrix, and then in this particular case we basically deleted this particular edge. And then we feed the same thing back to the same GCN network, and then you compare the output probability distributions on both, and the difference is bounded by basically an epsilon with a probability of 1 minus delta. So this is what we call epsilon delta differential privacy. So this is basically very well known strategy, particularly for this crowd, and so this is what differential privacy does. And so in the context of adjacency matrices, we're essentially perturbing one weight in order, or one edge in order to essentially protect yourself from disclosing the adjacency matrix entirely to your training platforms. So how do you perturb this matrix A to produce this adjacency matrix A prime? One approach is to essentially take your epsilon and delta parameters for your DP. You have your adjacency matrix. You generate a differentially private noise that is based on these two values. You add that to your adjacency matrix, and you generate a noisy adjacency matrix, and now you feed this noisy adjacency matrix to your GCN and then generate the output from that noisy adjacency matrix. But realize that this noisy adjacency matrix is very difficult to actually get because you don't really have a large variability here, right? You either have a 0 or a 1, connected or not connected. So essentially, anytime you're flipping them, you're essentially either deleting an edge or adding an edge. And so it's not like you're changing 3.5 to 3.4. It's a binary decision process in the case of GCNs. And so this is the fundamental problem. And in fact, this is exactly the approach that is actually taken by DPGCN, one of the well-known papers on differentially private graph convolutional networks. And there are also other approaches such as LPGNet. You can see the paper for more details for this approach. And so the question therefore is, what are the problems with these existing approaches? So if you look at these measured values in terms of their accuracy on the y-axis with respect to the epsilon, which is the differentially private values that we are interested in, the smaller the epsilon, the better the privacy. But the accuracy of the models such as DPGCN as well as LPGNet is substantially lower than these two blue and the green bars. This blue is essentially saying that, well, I'm just going to use MLPs. In other words, I don't even use adjacency matrix. And then the green bar on the top is showing you the actual GCN with no perturbation to the adjacency matrix. So clearly, you want to do at least as better as the blue, but as the epsilon values go to really small values like 1, 2, and 3, and 4, you're essentially lowering the overall accuracy of the model, in which case, why even bother using the adjacency matrix in the systems, and instead just drop that, right? So that's the goal. So obviously, we're not happy with that. So we want to try to get to a value of a small epsilon and still provide you a substantial accuracy improvements over this blue bar, and that's the goal of what we want to do. So to sort of summarize, DPGCN, basically A prime shares limited similarity with adjacency matrix A, because when you perturb the matrix, you're essentially transforming zeros and ones to zeros, and that's a substantial destruction. Yeah. I can't hear. I have to speak into this. Oh, okay. I thought I was loud enough, but I'm apparently not loud. And so, in the case of LPGNet, basically they don't use adjacency matrix at all. They use sort of a clustered graphs. Again, you see the details in the paper. So what are we interested in? We want to minimally perturb matrix A while producing the differentially private guarantees in the system. And so how are we going to do that? How are we going to minimally perturb matrix A? Here is one approach, and there may be other approaches, but I'm going to present the approach that we used in this paper. So we take the adjacency matrix A, and we're going to decompose the adjacency matrix A using a SVD decomposition. And so you have the basis vectors such as U and V, and the singular value S. So this is what we have. We can take from this, basically the matrix A, transformation of the matrix A into U, V, and a diagonal matrix S. And so now we're going to essentially take this approach, and then we are going to say that let's try to take advantage of this and figure out a way to actually reduce the amount of perturbation we're going to cause in your adjacency matrix. And so how will we do that? And so we're going to observe basically two important observations from this matrix. So we can do this for adjacency matrix A as well as for any adjacency matrix A prime. So basically you perturb one element and then do this all over again and see what happens to the matrices U and V in this system. So this data is showing you, the observation 1, is that A and A primes share the principal bases in a large real world graphs, and this is across a whole collection of graphs across many thousands of Monte Carlo simulations. You can see that U and V matrices that are produced from A and A prime, basically if you delete one edge from these very large graphs, the principal basis stays the same. So U and V basically stay the same in these two settings. That's observation 1. So keep this in mind, we're going to exploit that property. Observation 2. These matrices exhibit a highly low rank structure. And now this is no longer a new news because multiple papers have actually showed that, for example, if you're familiar with LoRa, which is a machine learning system where you actually exploit this low rank optimization. And so this is basically showing you for a variety of graphs such as sightseer and so on, there is substantially low rank in these matrices itself. And so we're going to take advantage of these two and create Eclipse in basically 3 steps. And so what are the 3 steps? So we're essentially step 1, we're going to basically extract the principal basis of A, which is what is shown before as before. And then second is we extract the singular values, and we're going to perturb just the singular values, because remember that U and V are shared between A and A prime, and therefore I'm going to take the singular values and just perturb only the singular values of this matrix itself. And so what does that mean? I basically generate a random noise, and instead of applying to the entire adjacency matrix, I'm only going to apply that to just the singular values in itself. And therefore, because I'm applying it across only to the singular values, I have the ability to control the amount of noise that goes into the systems, and therefore I can substantially reduce the amount of noise that is added to the adjacency matrices by themselves. And so now we are going to take this noise addition to just the diagonal matrix, we generate a new diagonal matrix S prime, and since U and V is shared by both A and A prime, we are going to apply this S prime to my adjacency matrix A prime and create basically A prime by using S prime U and V. And so essentially that's the step 2 process. Step 3, remember the second observation? The second observation is that there's a substantial amount of low rank properties in the system, and therefore we are going to essentially eliminate the ranks that are more than certain threshold. So for example, you set a value to be, I'm going to keep the first 10 low ranks or first 20 ranks, and then essentially substantially reduce the perturbation in the systems. And so when we do this approach, we essentially generate basically a new A prime, which is a prime on a low rank properties. And now we are going to use this A prime low rank as an input to our entire system. So now we are going to take the adjacency matrix that has been perturbed, but in a much more controlled manner, and we feed that to my graph convolutional neural networks. And so that's what we're going to do. And so now we do this, essentially A prime is all that a adversary can know, because we never disclose the matrix A to anybody else entirely in the system. It was never in the system. And so no matter what an adversary can do to the system, they can't actually extract the original matrix A in itself. And this A prime still satisfies the property of the epsilon delta guarantees that we mentioned for the differential privacy, provided the principal bases are in fact shared. And so that's an assumption that we made based on the empirical observations that we showed in the paper before. And so with that, the experimental setup is pretty standard. We use 6 different data sets, both for transductive and inductive settings. For those of you who are not familiar, inductive setting is much harder because you have never seen the graph, but you're going to try to predict from these unseen graphs. Transductive setting is where you have actually seen the graph properties before, and you're going to use that to query the system. We use different model architectures such as DPGC and LPGNet, and then we're comparing it with Eclipse in the system. And so what we can see is that the privacy utility trade-offs, Eclipse achieves better model utility over any of the existing prior works. And as you can see that as we, unfortunately my student changed the color, but this should have been blue, but this is the same blue as we showed before. But as you can see that the Eclipse is better than just using an MLP based mechanisms, and it actually is much better than any of the existing prior schemes that are shown in the Of course, there are more results in the paper, including various attack models and so on. So conclusions, privacy is an increasingly precious commodity. Eclipse is a privacy preserving GCN, uses SVD and low rank decomposition, and it works well across a whole range of data sets. And of course, I would be remiss if I don't show my students and my collaborator who worked on this paper. That's the first author, Ting, and then Yunye, and then my colleagues, Salman al-Smir. With that, I'm going to stop and take any questions you may have.
Thank you very much, Murali. Are there questions about the talk?
Hi there, super cool looking result. I just want to make sure I'm clear about one thing. So this doesn't truly satisfy differential privacy because it relies on this, you said on real world data sets maybe it has a stability property, but really worst case, is that right?
Good. So the assumption is certainly true that you have to have the basis of A and A prime must be the same. Otherwise, you can't reconstruct A prime and still hold the properties. So that's correct.
Okay, yeah. Have you considered using techniques like, say, smooth sensitivity or anything that would maybe like deal with the fact that most data sets are nice to make it bona fide differentially private?
So that's outside of the scope of what we have done, so I don't want to claim something that we don't know enough about. But I can certainly say that there may be other mechanisms to, as you said, some sort of smoothing of the large graphs to make this property hold true even when it is not necessarily true in some particular graphs.
Cool, yeah, thanks.
Thank you for the talk. I apologize up front if my question is going to be stupid. Perhaps I misunderstood here something. A prime is a neighboring matrix to A, namely they differ in only one entry. And differential privacy, the purpose in differential privacy is to add noise so that for any A prime, not a particular one, for any A prime, you cannot distinguish significantly between the two. And I got the feeling that in your process you have a specific A prime. Maybe here I missed something. Okay.
Good question. So basically, this idea of adding noise to the to the system by using essentially, let me show. So this approach. So where we are adding a differentially private noise, this is trying to simulate that particular process that A prime that is, remember, in order to actually generate A prime, I only have to flip 1, 0 to 1. That's all I need to do, or 1 to 0. That's all we need to do. But you have to do this like millions of times to actually get the right Monte Carlo-like simulation of different kinds of A primes. So what DP, differential privacy, does is it gives you a very simple tool where you can add a Gaussian noise to the matrix A and create that intuition of what you have to do with a million Monte Carlo simulations without actually doing the simulations themselves. And so this is basically one way to apply differential privacy without having you to do all these various sort of, flip one, retry, flip one, retry approach. And so essentially what this is doing is, this is exactly differential privacy as we would imagine, except the implementation is actually adding a Gaussian noise to the matrix A in itself.
So this is the Laplacian noise, yes?
Yeah. So this is the this is the noise that is adding to the adjacency matrix to generate the differentially private A prime in this case.
And then you round up for the closest 0, 1.
Yeah. So once you add the noise, this is the problem I was mentioning, is that because it's a binary decision process, and typically when you do differential privacy, if you have 13.5 and you perturbing it a little bit, you will get 13.2 or 13.5 or 13.7. Whereas here, 0 goes to 1 or 1 goes to 0. There is no in between. And that's the problem, is that when you perturb these matrices, you're not pushing them slightly back and forth. You're shifting them to zeros or ones all the way. And that causes a substantial perturbation to the matrices.
Thank you.
Just time for one more question, unfortunately.
I had a question. If the security guarantees between DP-GCN are the same as Eclipse, like DP-GCN, you're adding your DP noise to the A matrix, versus in Eclipse you're adding it to the SVD. And so, is your approach DP with respect to the SVD, or like how do you compare across the two?
Excellent question. In fact, so there are two things why our approach, even though it seems to be adding less noise, still gives you the same sort of guarantees. So I think that's the foundation of the question that you're actually asking. Yeah. So there's one critical reason, which is that when you're adding DP noise to the original matrix, as I explained to the previous gentleman, I'm either pushing the values to 0 or 1. And here, when I'm actually applying DP-GC and differential private noise to the singular values, singular values are not zeros and ones. They're actually real numbers. And therefore, my range of values in our particular simulations is somewhere in the range of 0 to 14. And therefore, we're actually adding noises to the values that are real numbers. So you're not pushing the zeros and ones all the way, you're actually pushing them slightly back and forth, and that allows us to get the singular value perturbations to be somewhat limited in range. And that is the fundamental reason why we are not perturbing zeros and ones.
Are you clipping the singular values? Like, do you have to bound the sensitivity of the SVD?
Yeah, so the sensitivity of the SVD is clipped to 2, square root of 2.
Okay.
And there is an actual mathematical proof shown in the paper that shows why that's actually the best way to do this approach.
Thank you.
I invite everyone to find Morale afterwards at lunch for further questions, and thank you once again for the presentation.